Okay, maybe I'll start with a slow introduction in the hope that, well, I should be exactly 3 minutes. Oh, okay, it's 3 minutes. So, well, it's my great pleasure to reintroduce Lev for another installment of his lecture course. So Lev, please take it from here.
Okay, thank you. So this will be the last one. This is kind of good news. So let me remind you that we're considering now a family of three-dimensional topological quantum field theories, which are B models based on moduli spaces of instantons. The number of instantons is varying and the group is fixed. Although for every R, we have its own family with which we can play. So this is a three-dimensional quantum field theory. We consider a spatial slice. So we consider a two-dimensional surface which represents space in three-dimensional space-time. And so to a compact surface, maybe with a boundary, one would associate a vector space, which is the space of states, Hilbert space, by certain rule. The two-dimensional space has certain inner structure. They're what physicists call defects. So this black line here represents a defect which separates domains with targets being instanton moduli spaces with different numbers of instantons. So as you pass through this red line from left to right, the number of instantons jumps. And this jumping is performed by a special Lagrangian correspondence between these two symplectic varieties. I will maybe a little bit later remind you what this correspondence is. Essentially, this correspondence is related to an edge in Nakajima quiver. So this picture in Nakajima's story would look like this. To a domain, you would associate a circle, another domain, another circle, and you connect them by an edge which is transversal to the black line. So in Nakajima's picture, this will be M, this will be N. The Nakajima quiver corresponding to instanton moduli space is a separate story. It's the other quiver. This is a story of two quivers. So in particular, M could be equal to 0, which means that the moduli space is just one point. So from the physics point of view, this is negligible. This is as if the space or space-time had a boundary here. So nothing happens to the left of the black line. On the right, you have a moduli space. So then on this black line, there would be a Lagrangian object or a fibration whose base is Lagrangian subvariety in the moduli space of instantons. So this is a special case. In Nakajima's language, that would be 0 and N, except that Nakajima never puts zeros. So if in this picture you consider a closed circle, green circle, which is for cutting, then, and this green circle may be crossed by black lines. So here is an important case when two black lines are entering and two black lines are exiting. By the way, let me remind you that orientation of black line is selected so that to the left of it, the number of instantons is less than to the right. And to a black line, you can associate local charge, which is the difference of instantons to the left and to the right. Let me call it local charge. So here we have a picture of a green circle, which is a cut. So to a green circle, one associates a category. Since we're in three-dimensional TQFT, one-dimensional submanifold is to a one-dimensional submanifold, you associate a category. So roughly speaking, this is a category of coherent sheaves over Nakajima over a close relative of Nakajima quiver, which is depicted here, of this quiver. As you see, there is no framing. The numbers n correspond to circles, and yellow or golden arrows show you the stability condition. So in this quiver, you have arrows going back and forth as usual, but to the arrow which goes along the yellow, for the golden arrow direction, you impose condition of highest rank. So Nakajima's quiver is dual to the picture of green circle with black crossings, as you see. And this category of matrix, so the actual category is the category of matrix factorizations, because Nakajima's quiver would be quite singular in general. So the category of matrix factorizations comes from defining this category as a home in the two category of two green circles, N1 and N3. So in other words, that's a two category associated to the product of two instanton moduli spaces between two objects, the lower part of the circle and the upper part of the circle. Let me put here two green dots with which I cut the circle into two semicircles. So each semicircle gives me an object, composition of Lagrangian correspondences. So you compute the home by standard procedure, which we have discussed before. So in these categories, there are four special objects. First of all, there is an object that a dot that you simply put on a black line, which defines an object in the category of a circle with two cuts. This corresponds to Jusis-Murphy or Bernstein-Lustig object, Bernstein-Lustig element in affine braids. So this is, well, let me say it here. You take identity object in this category. So this is just identity. And you tensor multiply it with a certain, character of the groups, GLM and GLN on both sides. So you tensor multiply it with a one-dimensional representation of GLM cross GLN with opposite weights. That's what it is. It's a simple thing. Now there are two more complicated matrix factorizations which we call plus and minus, and they eventually correspond to positive and negative crossings in the affine braid. And then we may also consider another important object in this category, which is related to Kazhdan-Lustig objects. The actual Kazhdan-Lustig object is built out of two of these special dots in this picture. Red marks the charge or the jump in the number of instantons on each line. So in particular, we're interested in green circles where one of the arcs is has no instantons, 0 instantons, as in here. So then if R is equal to 0, the corresponding category is almost coherent sheaves over derived Steinberg, equivariant coherent sheaves over derived Steinberg or derived Grothendieck-Steinberg. If R is equal to 1, 2, and so on, this is an interesting category of matrix factorizations, which we discussed before. And that's, so you see that the category itself is monoidal, because it's endomorphisms of this semicircle. It's the endomorphisms of semicircle, so it has monoidal structure, and that's where we send affine braids for any value of R, in fact. We can send affine braids in there. From this picture, we get, so this picture corresponds to a representation of the group of affine braids on N strands. So here I wrote that this is an endomorphisms of the object FLN. I dropped the R colored by 0 because it plays no role. And if R, the instanton group, is equal to 1, then this homomorphism factors through ordinary braids. And this we also discussed. So finally, here is a picture. Imagine an affine braid, which is generated by positive crossings, negative crossings, and Bernstein-Lustig elements. So all this picture is hidden inside the box called affine braid. And then we simply close the strands and strands around. So on the outside, we put 0, no instantons. So inside there will be n instantons, and there is this black point, black dot, which carries, I should have, did I miss it? I guess I missed it. For a green circle without marks. What is this? Sorry. A green circle without marks is more or less category of coherent sheaves over the corresponding moduli space. Again, up to minor details, especially important when R is equal to 0. So this to this one associates coherent sheaves here. And matrix factor, properly defined category of matrix factorizations when R is equal to 0. So if you consider a disk with a black dot inside it, then black dot must be colored by a sheaf over the instanton moduli space. So to this picture, we associate a vector space, which depends on the braid and on what you put on that black dot, what sheaf. And in particular, if R is equal to 1, so we use Hilbert schemes, and the dot is the sum of exterior powers, is colored by the sum of exterior powers of the tautological bundle, call it T, then the vector space is the link homology of the link constructed by braid closure. So let me now say a few words why there is a canonical choice for elementary objects that we discussed over here. These ones, the crossings.
Lev, can I? We covered this many times, but can you? But I still didn't quite get it. If you put some other sheaf there in the middle, why is this exterior powers of the tangent bundle are so much more special than some other sheaf?
This is so. Technically speaking, this is the one which guarantees the invariance under second Reidemeister move. Sorry, under second Markov move. So when you present a link by a braid, then different braids may give you the same link. In particular, it may, here is an example. So suppose you have a braid, and then you put an extra strand, and now you close everything. Just a moment. Yeah. So you see that in the middle, there is a loop, which you can remove. And so this is a braid on n+1 strands, the whole thing. Let me mark it by green. This is a big braid on n+1 strands, which contains an arbitrary braid inside it. So this braid gives you the same link as the inner black box braid, because you can remove the kink. So
well, I understand that, but suppose you started not from suppose you didn't know anything about knots, you just wanted to study the theory you're studying now. How do you see that that particular object is somehow distinguished? What distinguishes that particular object if you didn't know anything about the Markov moves? Or like suppose you were in higher rank, and so you're not talking about knot invariance at all, but is there still the best thing to put in the middle, or there is no good thing to put in the middle?
So again, there are two answers, technical and conceptual. The technical answer is that the Markov invariance happens because there is a desert in cohomology of linear bundles over a projective space. So if you take CPN and take various O's, there is a gap where they have no sections, and the reason why Markov holds is because you pick either O0 or you pick O minus n-1 in certain calculation. So in computing the vector space corresponding to the closure of the braid, you have to compute cohomology of certain Koszul complex, which extend from O0 to O minus n. So this is a good one because only O0 contributes. And then you can shift it by 1 to the left. So it will go from O minus 1 to O minus n minus 1. And then again, something good will happen because O minus n minus 1 has exactly one cohomology, one-dimensional cohomology. So you need this sheaf, you need to pick a sheaf which will exactly make this shift when you tensor with it. It's a little bit technical. Now, conceptual answer, maybe I will give at the end where I explain how this comes from string theory. So string theory says that you must put this thing in there because.
Oh, great. I look forward to that.
Oh, okay. Okay, so I should get there. Okay. It comes from a certain string, from a string stretched between a stack of D2s and a single D6. So it's preordained, so to say. It's not arbitrary. There is a reason why it happens this way. Okay, so let me explain why there are canonical choices for all these matrix factorizations over here. So there is a functor. Sorry. So there is a functor from the category where you start with 0 to the category where you start with k. So in other words, in this picture, you can add k instantons to every arc of the green circle. and there would be a function of adding instantons. So in other words, you can take this green one and superimpose and combine it with a green circle carrying K. So you glue them together and then you add K to every arc. So let me explain where, and therefore every canonical choice of black dot over here, and that's what we do, will generate canonical choice when you added K to everybody. And one way to explain it is to say that edges of Nakajima quivers with stability imposed are Hamiltonian reductions of GLN. So for example, the standard edge between M and N is take GLN. Well, you know that this is the equivariant cotangent bundle to Grassmannian, where the subspace is equipped with a framed subspace. So in other words, this is GLN, and you take a quotient over over the subgroup of these matrices. N minus M upper rows are arbitrary, and the lower right square is identity, and 0 in the lower left rectangle. I use now, in this picture of the quiver, I use solid blobs, meaning that I may later attach other parts of the quiver to these solid blobs. And when I draw a circle, just an empty circle, this means that I already did the Hamiltonian reduction and I will not attach anything else to it. So for example, this quiver with 3 vertices will be quotient of GLN by the following, by almost a hyperbolic subgroup, but you have to put identity in the lower right square. This is what you will get.
You mean parabolic?
Oh, yes, sorry. I'm sorry. I'm not very knowledgeable. I know the words to use, but okay. So let us, for convenience, let us introduce a star-shaped edge. Let me put it in quotes in Nakajima's story. So in addition to ordinary edges which connect 2 vertices, we will consider a star-shaped edge which connects 3 vertices. And to it, we will associate again I mentioned it many times, so we'll associate a Hamiltonian reduction of GLM plus N over the subgroup formed by these matrices. So this is M plus N, and here you have M and N. So this quotient has the left action of GLM plus N and the right action of GLM cross GLN. So this is a valid edge. It's the resulting variety is symplectic with the group action. In our physics picture, this means that I glue together 3 half planes. So this is now my quantum field theory is defined not on a smooth space, but on a smooth CW complex. So in this section, you see this black dot is where 3 subspaces come together to a single line. So in your space, you see a certain singularity, which is rather tame. So ultimately, we will get a foam, what we call a foam, a smooth CW complex. So here is a simple general fact. If you have a set with the action of the group and the group has normal subgroup, then taking the quotient by the group can be done in 2 steps. First, take the quotient by the subgroup, and then take the quotient by the quotient group. So now it's easy to check that Nakajima's age, which we just discussed, this one, can also be presented as a triple edge with empty circle on one of the ends, which means that I do Hamiltonian reduction on GLN minus M completely. There will be nothing else there. But N and M are free for gluing with other parts of the quiver. So on both sides, I get the same symplectic variety with the action of GLM cross GLN. And from our physics point of view, this means that these two pictures are the same, are equivalent. So I could contract this green edge, which ends on the arrow. I can contract it completely. And then the arrow will simply be cutting the green segment. And similarly, we can consider a longer piece of the quiver, 2 edges. And that would be equivalent to putting this triple edge, star-shaped edge, and then put Nakajima quiver combination on it. So this is the same as this, because they correspond again to the same Hamiltonian reduction eventually. Only the sequence of taking elementary quotients is different. But this latter one is the result of gluing together 2 quivers. So from our 2 categorical point of view, it's the result of taking home 2 categorically over the dot colored by N minus K. Yeah, so if you glue them together, then this is what you will get. Now, the point is that now you can compose this home with the home from one Nakajima quiver to another, from between these 2 simple ones. So this is what turns a crossing with 0 into the crossing with K. So in our picture, what I just said is that having 2 lines in parallel is the same. So if you have 2 black lines which interpolate between N and K, you can lift them on a separate strip attached at this black dot. And so you can cross them on that green strip, and then translate it into the crossing of black ones. So in other words, you can lift all the crossings to a separate strip attached to your main surface in a singular way. So this is what we get eventually. The crossing which we want to define can be presented as gluing over red segments. So here you see a red segment, 2 pictures on which black lines end. So there is one piece, and then there is another piece. Let me mark it like this. So this is where the space actually is. You just glue it and here everything is our space. So you glue them together, you get this singular what do you call this? Almost a cone built on top of this red thing. And so you lifted your crossing from extra K to 0 situation. So this is more or less the explanation why we have this functor f, and why we can translate a crossing from 0 to crossing from K. foam helps. Let me say a few words about the case with, let me take a 1-minute break, just a moment, I'll be back, sorry. Sorry. So here is what happens when we have framing. Consider this defect. So the Lagrangian correspondence is related to extra variables which are home from m-dimensional space to n-dimensional space, and there is also home going backwards. So this home phi is supposed to be of highest possible rank, no kernel. So if we have a non-trivial framing r is bigger than 0, then we impose a conormal. Sorry, first of all, if we want to use stability that phi from m to n is of highest rank, then it looks like we have to use stability for the inner quiver related to covector rather than the vector. So our stability is that W dual to W generates everything rather than V, or I and J. Nakajima uses I and J. So we have to use the other condition. And because then phi will take dual to phi will take, which is also of highest rank, will take W from the right to W on the left. So it will bring W backwards, and I could impose condition that Wm is phi is dual to phi applied to Wn. So in other words, the framing in the highest n will determine the framings in the lower n regions, in the lower instanton number regions. Then everything will work fine. Everything we constructed there will work fine. So the outer framing, the inner framing has to be carried from high to low. And in order for this to work, you need an agreement between stability condition of the outer quiver and stability condition in the inner quiver. So the GL1 2 tilde story in this language looks as follows. Consider an affine braid, beta, and we have 0. So now we consider a theory with r equal to 0, so no framing for the inner quiver. So to this picture, we associate, so this picture creates a coherent sheaf or a complex of coherent sheaves on the green circle, which is Chern character of the matrix factorization associated to this braid. That's what we considered before. So roughly speaking, again, closure of an affine braid creates a complex of coherent sheaves over the commuting variety. But honestly, and from the technical point of view, this is important, we create matrix factorization over cotangent bundle to GLN across the group with this superpotential W. But now inside that green circle, you see we have an annulus with the red boundary. So we extend our story farther inside to the red circle. Now we consider a domain we consider space where we have instantons of UR, and there is another green circle. So we will glue these two green circles together. So we have this second annulus, and to its middle circle, we will glue perpendicularly the first picture. So in the section, this is what you will see. There is a green segment from M to M plus N. But at the red dot, we also glued the cross segment from the top picture. So this is just to explain.
Lev, so when you draw this kind of CW complexes, are we supposed to really think about them as a space or some space-time theory, or is that supposed to?
Yes.
And that is, in your opinion, and in your expert opinion, that is well defined on such singular spaces.
I'm sorry, say it again.
And in your expert opinion, this is well defined on such singular spaces.
Yes. So the point is that if you have a quantum, as far as I understand, if you have a quantum field theory which admits boundary conditions, so you can define it on manifolds with boundary, and that boundary is genuine boundary, not because you cut it. Then usually you can also define such a theory on CW complexes, where, for example, if you have a two-dimensional theory which admits boundaries, or even better, a family of similar two-dimensional theories admitting boundaries, then usually you can also define a theory on a two-dimensional CW complex, which is smooth. So a vicinity of a point is either, well, let me make this comment. So a vicinity of a point is either usual neighborhood of a plane, or it's a junction, for example, of two or more subspaces, like this. So here is your point. Or the vicinity of a point is a cone of a graph. So suppose you have a graph, and then you build a cone on top of it. So you have many edges, and they all come to your point. And you can define a structure of topological quantum field theory. So this is what we use. We use it in the story about link homology under the name foam. But it seems that these foams also appear in Langland's story, and as I will explain in a few minutes, this is a dimensional reduction of the Langland story. So you could extend this to Langland's duality story as well, and it seems to be natural. So as you see, it shows that you can glue a braid living without, where there is no framing, by adding this adds instantons in the presence of framing. So again, here we have R, and here we have R. And here we have R equal to 0. So this way, sheaves over commuting variety give you a correspondence from M instantons to M plus N instantons of rank R. Again, this can be done, as far as I understand, this can be done very rigorously from the mathematical point of view if you use the language of matrix factorizations.
Well, in general, if you have some correspondence, means you have a sheaf and a subsheaf and a quotient. So anything you have an object on the quotient, this will define your correspondence between. So that would be, but you're saying that this is so. So in mathematical, you can have like a variety of triples when you have a sheaf, whatever sheaf, subsheaf, and a quotient, which has a rank of 0, and then that way you create. That's kind of like the triple vertex there, the red dot. But but you're saying that there's actual space, the actual singular space on which this stuff lives. That's pretty interesting, yeah.
So physically, yes. seems that this is possible and convenient. Okay. So again, I talked to various people and to Alexei many times about what is the status of using sheaves over commuting variety to create this correspondence. And it's, again, it's not clear to me what it takes to define it properly without matrix factorization.
No, it's absolutely defined. Like I said, there is a stack of triples, and anytime you have this is really corresponding in 3 spaces. And anytime you have anything on the rank 0 things, you can pull it back and you can use it, you know, push forward. That defines the correspondence.
Okay. Because okay. So let me comment about 4D origin of these pictures. So this comes from a combination of 2 papers, or actually 1 plus many. There was a well-known paper by Kapustin and Witten about Langland's duality. They explained that Langland's duality comes from a certain duality of a 4-dimensional n equal to 4 super Young-Mills theory with a topological twist, with a particular topological twist, whatever this means, which means that the actual theory is topological. And then there were 3 papers by Guyot and Witten, again, pretty old, in which they considered boundary conditions which respect half of the supersymmetry in these theories. So the boundary conditions of Guyot to Witten could be put in the topological twist of Kapustin-Witten, and this tells us, mathematicians, that Langland's duality is, so in Langland's duality story, you take, at least old, as far as I understand, you take a Riemann surface and the group, and to this you associate a category. So this can be enhanced. On the Riemann surface, you can draw lines, which will be crossings of, so this Riemann surface is a 2-dimensional submanifold in a 4-dimensional manifold. But now this 4-dimensional manifold can be enhanced by codimension 1 defects, which are these Guyot-Witten boundary conditions. In fact, they're defects. And so they will cross your...
I'm a bit confused. So the pictures we had before, that was a space or something 2-dimensional inside 2 plus 1, right? So you had something 3-dimensional, and then you add 1 more S1, so it's like you had the Riemann surface cross S1, or what is?
Just a moment. So sorry, let me say it properly. So in the Kapustin-Witten interpretation of Langland's, you consider a 4-manifold, which is a product of 2 2-dimensional manifolds. One is compact and the other is, they call it, no, actually the other way around, because C is for compact. That's their notation, if I can remember it correctly. So something 2-dimensional. Sorry. So something 2-dimensional cross something else 2-dimensional. And then they say, let's assume that this C is very small, compact small. Then the 4-dimensional theory will become a 2-dimensional. So this is a 4-dimensional twisted blah, blah, blah. Will become a 2-dimensional theory on this sigma, which depends on the choice of C. And now they say study its category of boundary conditions. And that's the category which Langland's people associate to C. That's the logic of their paper. Now, Guyot and Witten say that inside that M4, you can insert three-dimensional submanifolds. So they will place them so that they cover sigma and create lines on C. So on C, you will have lines of two types. One type is called NS5 and the other type is called D5. And they can cross, and so cross whole sigma. You can place them like this. So then the resulting theory on sigma 2 will depend on how many lines you drew on C and how these lines were crossing and so on. And the theory and the category of boundary conditions in this case will also have a partner on the Langlands dual side. In particular, you'll have to switch NS5 to D5 and D5 to NS5. That's part of the story.
So which of the surfaces we saw, that's C or sigma?
I'm sorry?
The pictures you were drawing before.
Yes, the surface that I was drawing before is in fact a three-dimensional thing. So let me explain. So take all the pictures that I was drawing and multiply them by S1. Everything. Maybe except that dot. Maybe except the dot that I put in the middle. I'm sorry. Yeah, the dot you do not multiply by S1, but everything else you multiply by S1. So to make things simple, suppose that you imagine that we were drawing identity braid. So you would have this disk, and then you would have another line and another line. So you have 0 on the outside, 1, 2, 3. So this is a valid disk. Multiplied by S1, you will get a solid torus with a layered boundary, because the disk has layered boundary. Imagine that all these circles are close to each other. So the solid torus will have layered boundary. So this is the solid. So this solid torus is the space of the Kapustin-Witten story. So it's a space of a four-dimensional quantum field theory. Again, to that you associate a vector space of states. Now we used to associate categories to green circles. So there are two types. So here you could have, for example, a green circle here. So this green circle will become a green cylinder. So it will become C2 in the Kapustin-Witten theory. So this green circle will become a green cylinder. But our category of the circle is not the Langlands category associated to a torus, and I will explain in a moment why. So you would think that our green circle should correspond to the Langlands category of T2, but there are two, but there will be two red meridians drawn on it. And also we could have, for example, this segment, we could have this green segment from 0 to 0. I don't have to, I could extend it like this, but nothing is in there. So this would become an annulus in the, this would become an annulus in the Langlands story, because again, you multiply this segment by circle. So this would be an annulus. But this, just a moment. What's the proper way? I'm sorry. Yeah, there will be There will be many, many red lines. What I drew here in black isn't, okay, I could draw them in black, but these are still the Gayot-Witten defects. So there will be many, many defects going along this. Many, many, many defects. So to that, we also associate a category. So the category, the coherent sheaves over Steinberg variety thing, or matrix factorizations in the presence of framing, and the categories which we call Drinfeld centers, they're all categories of Langland's type, except that Langlands didn't draw, geometric Langlands didn't draw lines on the surfaces. So geometric Langlands considered only surfaces without lines. So these lines, so the black circles in this picture become cylinders in the four-dimensional picture in Kapustin-Witten's story, and these are NS5 cylinders. So they become NS5 cylinders. But in addition to that, there is something else which you do not quite see. Where is the other quiver, the inner quiver? Now you can see the inner quiver. So the solid torus, in addition to having layered boundary, it also has two defects which cross through it. I drew them in red in this picture. So there is an NS5 defect, and then there is a stack of D5 defects, RD5 defects. You can draw them in parallel, close to each other. So now, if you go along the dashed green line inside that solid torus, you see the affine quiver. And if you go from, well, how should I draw it? Say you begin on the boundary, and then you go inside and come back to the boundary. This kind of trick. So you cut through the layered boundary twice. Then to that green segment, on that green segment, you will see the, for example, linear Nakajima, AN-type Nakajima quiver, which gives you Steinberg variety. So just again, imagine a solid torus with layered boundary. So you have concentric tori called NS5, and two cross sections, one being NS5 and the other being D5, or several D5s. And that's the four-dimensional origin of what we're doing. So our story is compactification of this story when we assume that S1 is very short. So when S1 is very short, we do not see the red NS5 and red D5s. They're all sandwiched. But we still see the layered boundary in the form of circles. So again, all our categories associated to green sections are Langland's categories associated to these sections cross S1 in the presence of these extra line defects. Andrei, do you want to ask anything or comment or say that it doesn't make sense, or should I draw another picture?
Not sure, Lev. I think it's best if you continue according to your plan.
Okay.
At least is that, am I correct in understanding that all these pictures we saw before, they were in the curve you called C?
No. The curve C, sorry. So if you want to know what is curve C, take any green circle or green segment and multiply it by S1. And this will give you a, do you want to call it a curve? I guess you want to call it a curve. So it's real dimension 2. Then you will get something of real dimension 2 to which Langlands associates a category. And as you see, we also associate categories, but to one-dimensional green things. Our green things are one-dimensional. When you multiply them by S1, they become two-dimensional.
Okay, thank you. That helps, yeah.
Okay. Okay, so maybe before I comment on strings, I try to comment on strings and why this is related to strings. Let me make, it won't look pretty, but move it. So part of it will move away. So what are the variations on the game that we're playing? So the variations, when we have, so two variations, two stories. When we have these lines and domains between them, we do Hamiltonian reductions. So here we have mu1 coming from here, and we have mu2 coming from there, and here we have x. And so we write W, which is X, or trace, of X times mu1, plus or minus, depends on your, let's say minus mu2. This is part of the story. So we could play with the story a little bit by adding here a constant. We could add here a constant times identity matrix. So this would change all our categories. And this is what people in the link homology business call Wi-fication. So if you ever hear about Wi-fication, it means that we reduce not to zero moment, but to constant times identity. And game number 2 is when, recall that this thing is an object in the two category of M and N. But what if you apply Legendre transform? Another game you can play. So this gives you a new kind of braid strand. I mentioned this, and you get interesting homology out of it. So that's another game you can play, variation on the subject. Okay, now let me say as much as I can about string interpretation. And again, this should be told by experts, but so I'll try my best. So there is M theory, which is 11-dimensional supersymmetric quantum field theory, which means that the theory is defined, it associates numbers to 11-dimensional manifolds and to 10-dimensional manifolds, which are spaces. It associates a vector space of states. Let's call it M10 hat. In this theory, in this 11-dimensional space-time, you can place objects, or defects if you want, of dimension 3 and dimension 6, which are called M2 brane and M5 brane, because these are their dimensions when you intersect them with spatial section. That was decision of Polchinski. So when you hear M2 brane, it's a 3-dimensional submanifold. Now we consider So everyone should read the paper by Andrei and Nikita on 11-dimensional theory. Where they argue that one should go beyond what I just wrote here, but let's stick to this simple case. So let's consider the space-time of the following form. A three-dimensional Calabi-Yau. Wait a minute, how do I spell Yau? Is it O or U? I'm always, okay. Times, let me call it CY. Times something of real dimension 4, which is hyperkähler, times just R, which will play the role of time. So our space is three-dimensional Calabi-Yau times two-dimensional hyperkähler variety. Now, we assume that Calabi-Yau is compact, in quotes. It's not compact, but interesting things happen in a certain compact domain. So let's pretend that it is compact, although it's not. And let us take the hyperkähler variety to be C2 with a funny metric. It's called Taub-Knot space. To be honest, one has to take metric into account in these constructions. So since our Calabi-Yau this Taub-Knot space has a group of isometries, which is, if I remember correctly, SO3 cross U1. Now, if you wonder what is this Taub-Knot space, what its geometry looks like, imagine R4, C2 is the same as R4, and fiber it by three-dimensional concentric spheres. Now, as you go away from the origin, the spheres grow in usual R4. But three-dimensional sphere can be fibered over two-dimensional sphere. It's called Hopf fibration, with a fiber being a circle. So in R4, as you go away, everything grows linearly with the radius. The radius of S2 grows, and the radius of S1 grows. So in Taub-Knot, the radius of S1 doesn't grow linearly. Rather, it has a limit. It becomes stable. So eventually, as you're very far away from the origin of this Taub-Knot, you see a large S2 and a fixed radius S1 fibered over as a fiber over it. So that's what Taub-Knot is. So if you go radially from the center and look at these circles, they start at radius 0, and then the radius grows and stabilizes. So such a thing is called a cigar in physics lingo. I think it's Witten's name. Okay, so since Calabi-Yau is small, we may ignore it, and so we get effective 5-dimensional quantum field theory on Taub-Knot cross R1, and that's what we want to study. So it's a complicated theory, but we will look not at all the particles that may exist there and their interactions, but rather we will look at the special particles which are called BPS, and we'll look at their states in quantum mechanical sense. So our space is Taub-Knot and time is extra fifth coordinate. Now, what are these special particles? What does it mean? So I will give you an analogy to give you a flavor of the meaning of these BPS particles. Consider a compact manifold with a metric in differential forms, and there are three operators: the de Rham differential, its conjugate delta, and their anti-commutator, which is called Laplace-Beltrami. So they form the simplest example of supersymmetry algebra, d and delta squared to 0, and delta capital Laplace is their anti-commutator. So the hard question would be to find the spectrum of delta. That would be similar to asking about all the particles in the 5-dimensional theory. It's similar to asking about the spectrum of a Laplacian. An easier question is to count the zero eigenspace, count the harmonic forms on M. Well, again, finding them may be hard, but counting them is usually relatively easy because these are given by Betti numbers. Now, in many in special calculations associated to M, which involve counting of all the differential forms, it may happen that the contributions of differential forms with non-zero eigenvalue of Laplacian will cancel out because such forms come in pairs related by d and delta, going back and forth. So in certain calculations, they cancel. And then you're left, you just have to pick up the contribution of harmonic forms, which do not come in pairs. They're single because they're killed by d and by delta. So BPS particles are the analogs of harmonic forms. And there are certain quantities in which the contribution of all the particles equals the contribution of just BPS particles, because the other particles come in pairs and somehow cancel each other in these pairs. So that's why physicists love BPS particles. So we want to count the states of BPS particles. Now, the Taub knot has a symmetry SO3 cross U1. So let's pick a subgroup U1 cross U1. The first U1 simply rotates the circle. And the second U1 is the diagonal subgroup of SO3. And the counting of all the particles together with these weights is reduced to the counting of BPS particles. And this is how you get, again, if you ignore the second U1, it's refined refers to somehow counting for the second U1. Then you get what's called as Gromov, Witten, Donaldson, Thomas, Panhari, Pandit, Thomas, and so on, invariants of the Calabi-Yau. Sorry. Andre?
I think we lost your screen. Yeah, so.
Oh, that's what. Just a moment. Sorry. Sorry. Oh. There. Sorry. Okay. So the famous invariants of Calabi-Yau appear as certain counting of particles in the five-dimensional theory in which all the particles except BPS cancel out. Now, the funny fact of M theory is that these BPS particles have the following origin. They come from these M2 branes, which are three-dimensional. So suppose your Calabi-Yau is a local curve, which means it's a sum of two properly chosen line bundles over sigma. And then this M2 will wrap on sigma on the zero section. So that's 2 dimensions. And it will be a point in Taub knot, and it will extend as a line along time. So from the point of view of five-dimensional theory, you get a line, a world line of a particle. So that's the origin of BPS particles. You have to count special two-dimensional submanifolds in your Calabi-Yau. Now, doing the actual calculation, it sounds easy, but the physics, the vibrations of M2s is a hard thing to describe. So it's better to go from 11 down to 10. In other words, we assume that our 11-dimensional space-time has a U1 symmetry, and the orbits of this U1 action are of limited size, even better of small size, to be honest. So then we can take a quotient by the action of this U1 compactify. So in other words, we assume that they're very small. And then we'll get a 10-dimensional manifold, which is the quotient of this 11-dimensional by the action of U1. And on this 10-dimensional manifold, one gets a string theory of type 2A. So this is much better understood by physicists because they can say what are elementary fields. So you have to, in order to describe the physics of this theory, you have to take path integral over these, over the world surfaces of the string. So in this theory, we have two-dimensional surfaces, which we call F1, for example. These are strings. Then there are NS5 branes, so these are submanifolds of dimension 6, and there are D branes. N must be even, so they're all of odd dimensions. So D branes of various odd dimensions, NS5 branes which are 6-dimensional, and strings. Where do they all come from? Strings and D2 branes come from M2 branes, depending on how U1 acts on this 3-dimensional submanifold M2. If it loses one dimension, then it becomes a string. If it doesn't lose a dimension, then it becomes a brane D2. The physics of both is very different. If M5 does not lose dimension, it becomes NS5. If it loses, it becomes D4. And if U1 action has a stable point in the vicinity, it looks like C2 with weights 1 and -1, and it doesn't touch the other directions. Then the compactification creates a brane D6 at the center of R3, which is the quotient of C2 by the action of U1. Now, a stack of coincident D branes is an ether. So if you took physics at school, then they told you about Michelson-Morley experiment, which proved that light and electromagnetic waves are not vibrations of a substance. So people thought that light is a wave. What is a wave? It's vibration. So what is vibrating? People thought there was special substance called ether. But Michelson and Morley showed that this ether does not have a rest frame. So any substance has a certain frame where it doesn't move. So ether does not have such a brane, so it does not exist. So now you're trained in thinking that light is an abstract thing, nothing is vibrating. So in string theory, a stack of these D branes, so if you take several D branes as pancakes and keep them close to each other, this is what ether is. So it exists. The meaning of its existence is that it's a submanifold, so here it exists and here it doesn't exist. So it's philosophically meaningful. Now, this ether vibrates. Why does it vibrate? Because strings attached to this ether represent particles which are the vibrations. So when you quantize, a vibration must become a particle. And this particle is the string attached to these D branes. That's the logic. So an open string may have its ends attached to D branes. So here I gave a picture. Now a string may vibrate along the stack or transversally to the stack. So if it vibrates along a stack, it describes vibrations which are along the stack of these D branes, and this is described by connections, UN connections on this submanifold, which is the stack of D branes. And if a string vibrates transversally to the stack, then you get a scalar particle, because you do not see these directions, so you get a particle without, which is not a vector, no direction. And these particles are in adjoint representations of UN. So they're wave functions are sections of a UN bundle, of a joint UN bundle. So a field of that particle, which, so suppose there is direction I transverse to stack of branes. The corresponding vibration is described by a matrix, because as I said, the particle is in a joint representation. So you get a square matrix. And the eigenvalues of that square matrix are the positions of the branes as they vibrate in this transversal direction. So the mathematical idea of describing positions of points as eigenvalues of matrices is reflected in string theory in this way, that this matrix is a field associated to vibrations of a stack of D branes. Okay, so now there are three choices of compactifying our Calabi-Yau, let's say, local curve cross Taub-Nut cross time. So first choice is, let us assume that time is a circle, and it is a small circle, and U1 will be rotating this circle. In this way, your 10-dimensional manifold will be Calabi-Yau cross hyperkähler variety. Now you lost your time, so you lost your individual particles, but particle counts are still with you. And counting particles will amount to computing Gromov-Witten invariance of the Calabi-Yau. But you will not see vector spaces because you lost time. You used time for compactification. If you want particles, do not compactify time. Then there are two choices. Choice number 2, which is very popular, is when you use the U1 symmetry of Taub-Nut. That's the symmetry which rotates the circle, whose radius has a limit as you go to infinity. It doesn't grow. So you have compact orbits. That's what you want. So you take a quotient. Taub-Nut becomes R3. You get a D6 brane because there is a stable point at the origin, which covers your Calabi-Yau. M2, which was wrapping sigma, didn't lose a dimension, so it becomes a stack of D2s. So now imagine your local curve. Sigma is covered by a stack of D2s, and they're vibrating along the fibers of the line bundles L. So counting these vibrations, as far as I understand, amounts more or less to counting quasi maps that you like. Now, quasi map from sigma to Hilbert scheme of C2. Now, the Hilbert scheme comes as T star of GLN cross T star of CN with the quotient. Now, why would, so the matrices X and Y from Hilbert scheme come from describing vibrations of D2s along L1 and L2. But what about the framing? Where does the framing come from? Why is it a Hilbert scheme rather than commuting variety? The answer is that the framing comes from D6. So we compactified by rotating Taub-Nut. There was a stable point at the center, which created this 7-dimensional subvariety, which covers the whole Calabi-Yau. And then there is a string which begins on D6 and ends on the stack of D2s. So this gives you the fundamental representation of UN associated with the stack of D2s. That's the framing. Now, there is a symmetric mirror symmetric choice of U1. Instead of rotating Taub-Nut, let's rotate L1 plus L2. Why not? Then you will get D6, which wraps Taub-Nut cross sigma. M2 still become D2s. Now these D2s support the 3-dimensional B model, very similar to what we're doing with Alexei. So now you can count the same invariance of n vector spaces associated to local curve by looking at the vector space of a Riemann surface of D2s wrapping sigma. So when in papers of Hausel, for example, and other people, you see some formulas involving counting sections of Hilbert scheme, this means that they use this compactification. Okay, so now I go to the substance after this warm-up. Witten and Waffa, I think, in part, discovered the following. If your 11-dimensional manifold is T star of a 3-dimensional manifold, which is locally possible, and if M3 is S3, this is totally possible. Cotangent bundle to S3 can be given a structure of Calabi-Yau. Cross Taub-Knot, cross time, and you put a stack of M5 branes, which wrap 0 section of T star M3. They wrap a cigar in Taub-Knot. So they cover those. And if you think of Taub-Knot as C2, they cover one of the 2 C's of that C2. That's what the cigar is, one way to think about it. And they extend in time. So that's one thing. And for a knot in M3, take its conormal bundle in T star M3, combine it again with cigar or anti-cigar in time, and this gives you another M5 or several M5s if instead of a knot you have a link. So now if you look at BPS particles, if you count BPS particles living on these cigars, which are the tails of M5s in the Taub-Knot, then that counting is given by Chern-Simons invariance of your knot inside M3 with the gauge group UN, where N is the number of M5 branes. So in particular, if you compactify your time, then the partition function of the resulting theory will be Witten-Rishtikin to Rive invariant. So in particular, if, okay, here I say the same thing, essentially. By the way, for the knot, you can choose between cigar and anti-cigar for the tail of your M5. So M5 must be C in that Taub-Knot C2. So you have 2 nice choices for each component. And this corresponds to Legendre transform in what I mentioned. So Waffa observed the following thing, that from T star S3, you can go down to O minus, you can change it to O minus 1 plus O minus 1 over P1, a particular local curve of P1, which is also Calabi-Yau. Then the M5 branes, which gave you N for Chern-Simons theory, for UN, they disappear. They are remembered as, roughly speaking, the size of P1. So now your N naturally became a variable instead of being a non-negative integer, which counts the number of branes. Now it turns into a size which at least you may hope to be a variable. So what happens to conormal bundles to the knots? That's a delicate question. So different people did different things with them. But there was a particular work of Blomkov-Schende who noticed that Hopefully PT polynomial of torus knot is related to certain counting inside Hilbert's scheme of a singular curve, and that inspired Diaconescu-Schende-Waffa for a nice physical paper in which they put these conormal bundles on the Waffa side, meaning on the local curve of P1, into a particular position. So our main conjecture is that this construction works not only for torus knots, but works for any grade closure. So here is what happens physically, and this is what will give the calculation that Alexei and I were doing. Consider the vicinity of the north pole of P1. It looks like a product of 3 copies of C. One C is the fiber of the first O-1, and the second 2 is a non-traditional split of the second fiber and P1 itself. So for simplicity, you may assume that C2 is second fiber and C3 is P1 itself, but I'm not quite sure that this is how it works. So ignore C3. The M5 branes will cover this C3, just ignore it. Project C1 cross C2 onto C1. C1, by the way, that's where the disk is where we draw pictures. So in this C1, you see these black lines. Lift them to the C2. So each point of a black line now becomes also a point in C2. So as you go along the closed braid, which we draw in our pictures, the lifted points in C2 start braiding. So this is how these Lagrangian submanifolds and local curve look. The radial order of these points in the second C2 should match their radial order on the C1 towards the center, if you want to get the standard stability conditions for the outer quiver. If you want the map from low C to high C to be of highest rank and not backwards, then the order should match. So M2s, which produce BPS particles, lie as a stack in the first C1, but they're lifted along the second C2 by various degrees. Now there are 2 choices with U1 compactification, which give you Langland's dual pictures of homology. So our choice is using U1, which compactifies local curve, Calabi-Yau. So it's a U1 rotation. It must preserve the Calabi, sorry. What is this? Oh, sorry. Just a moment. Sorry. So this U1 action must, in the vicinity of the North Pole, acts with weight 1 on P1, and with weight -1 on P1, and with weight 1 on the fiber of the first line bundle, first O-1 at the North Pole, and weight 0 on the second, on L2. So this is O1 at North Pole, and does not rotate L2. So at the South Pole, it will work in the opposite direction. So when you compactify, your M2s become a stack of D2s, because lying in the fiber of L1, so this is a stack of D2s, as many as there are strands in the braid. And the remaining 2 C's become R3. So ignore R2 and watch a single R in the transverse direction. So you do not see the position of braid points, the angular coordinates of braid points, but you see their radial positions. And the individual pancakes must match the individual positions of NS5 branes. In fact, sorry. This is what you see. So this is the extra R, and this is the C1, and so this is what you see. But when they project down, So we see only C1. We do not see this extra R because we see only the D2s. We see the black lines. So the black lines are projections of these points down. So the points interchange. Again, the order of points radially should match their order radially along R, or go in the opposite direction. Again, let me skip that. And when you see two strands braid, they come to the same level in R, and they come to the same position in the stack, but they do not cross because there is also angular coordinate, which we lost when we applied compactification. So we see only the radial movement of the braid points. But even that we do not see because it's the topological nature of the resulting theory of D2s is such that the radial position is not seen directly. Therefore, the description of braid crossing is mysterious. It's a matrix factorization that you more or less have to guess. You do not see it. Now, the origin of the sheaf, which is related to a degree, is the following. And there I will finish. A degree comes from the fact that in addition to the D2s lying in the fiber of L1 at North Pole, you may have another, M2. So these are M2s, a stack of M2s, which end on NS, ending on M5s, related to the braid. But in addition, you may also have M2s wrapping P1. And they will be intersecting at the North Pole, and they may form bound states, whatever this means. So a degree is related, a degree or variable a in Homfley-Petit polynomial reflects the number of M2s wrapping P1, which attached to our stack of M2s in the fiber of L1. So that's the origin of a degree. Now, when you compactify, P1 becomes a segment or an arc because our U1 rotates P1. Here we have our D2s, so M2 became D2s, a stack of D2s. But at the South Pole, there is also a stable point under the rotation, and this generates a D6 sitting over here. So the M2s, which were wrapping P1, become strings going from D6 to D2s. So as you see, they're fundamental in the GLN because they may end on each pancake in the stack. So they're fundamental in GLN and one dimensional at the other endpoint because there is only one D6. So careful analysis shows that their states are the exterior powers of the tautological bundle. So this is the space of states of the string stretched between D6 and the stack of D2s. That's what it is. That's what it represents. As you see, it is attached to the stack right at the center. So to summarize, Andre, you are studying D2s wrapped on your curve. So if you have a local curve, you study D2s wrapped on that curve, for example. And we're studying D2s which sit in the fiber of the bundle, of one of the line bundles. And what holds them there is that they end on Lagrangian submanifolds coming from M5. But when you do compactification, then your Calabi-Yau becomes 5-dimensional. I think if you add time, the 11th time, now you get something 6-dimensional, which I think is still Calabi-Yau. And then your 3-dimensional now NS5s become 4-dimensional. So I think this matches what you told me about relative invariance in relative Donaldson-Thomas invariance of Calabi-Yaus. So in a sense, I think we're counting also, one may say that we're counting a relative Donaldson-Thomas invariance. Your comment a week ago about trying several matrices maybe corresponds to a situation where instead of Taub-NUT as hyperkähler, you use cotangent bundle to a curve. I think that may give us what you suggested, but this requires more careful study. Okay, so I think I should finish here. And that's as much.
All right. Questions?
Again, if I wanted to relate to what you're doing, as far as I understand, I should learn much more and should understand it better. So first of all, the games that you play with the Mina are on the Witten side. So when you, as far as I understand, so it's on the side where you have T star of S3, which is not exactly S3, but at least it is on that side. On this side, what you want to do is to move, is either to play with framing and move the equivariant parameters related to framing's global symmetry, or you want to have in a fine quiver with many circles and play with stability conditions associated to those circles. So we could incorporate that from physical, at least from physical point of view, but with the topological twisting that we use, it's not clear if we can successfully move the pieces that you move. So there are some question marks. So I'm trying to move closer to what you're doing, but there's certain obstructions. In addition to, I have to understand much better what you do. But the Yification that I mentioned seems to be very similar to a set of, I forgot, you call them dynamical parameters. These Ys are Kähler parameters of the, these Ys are parameters of complex structure of deformed cotangent bundle to flag variety. So again, it's somewhat similar to what you like to move. But again, this
you don't have to adjust. You don't have to adjust your material to your perceived ideas to what I like, what I don't like. Let's see if the participants have some questions, or is it everything is clear? Well, I don't know. Maybe everybody's just digesting the. I would suggest we all give Lev a big round of applause for this monumental work of giving us these 6 lectures, and so I think we're really grateful for that. So maybe we can all give him give him a
That
big round of applause. Yeah.
Thank you for listening and for all the questions that you asked. In particular, your suggestion about many matrices certainly deserves consideration.
Thanks again, Lev. And for a few weeks, I think will be a break in the seminar. While the semester, when semester restarts, then Sam will be, who's not on this call, I don't think, but anyway, he will be. He's up in the queue for speakers in the seminar. But that will be in a couple of weeks once the semester starts and we have a kind of a stable audience involving the first year students, and then we'll restart. That will be communicated separately. And thanks, Lev, again, and thanks everybody for well.
Thank you.